Hello everyone. So we are from Group 9. Our topic for this presentation is carbon storage in basalt formation. This is our team members, Luqman Hakim, Hareez Imran, Muhammad Hakim, and myself, Bryan Russel. So for our content, we have introduction, injection of CO2 into basalt, the kinetic of mineralization reaction between CO2 and basalt mineral, analysis of long-term stability of CO2 in basalt, case study and conclusion. Alright, so for basalt, basalt is a type of volcanic rock that is formed from the solidification of molten lava. It is an igneous rock, meaning it is formed through the cooling and solidification of magma or lava. Basalt is one of the most common rock type on Earth, and it can be found in various locations around the world, both on land and under the ocean floor. Basalt is known for its dark color, typically ranging from black to dark gray, and its fine grain texture. It is composed mostly of minerals such as pyroxene, plagioclase feldspar, and sometimes olivine. Basalt can have a range of composition, but it is typically rich in iron and magnesium and low in silica. Basalt also has important geological significance. It is a common rock type in volcanic regions and is associated with volcanic activity such as volcanic eruption and lava flow. Basaltic lava flow, in particular, can cover large area of land and create extensive basalt plateaus, such as Columbia River Plate in United States and the Deccan Traps in India. These plates have significant impacts on the local landscape, ecology, and geology. For the fracture pattern, complex fracture pattern in basalt formation, being a product of volcanic activity, showcase intricate fracture pattern that play a pivotal role in the storage and migration dynamic of CO2 plumes during carbon capture and storage initiative. The complexity of this fracture pattern introduces a nuanced aspect to the geological consideration of CO2 sequestration. Understanding the spatial distribution, orientation, and connectivity of fractures in basalt is fundamental for optimizing the storage capacity and containment efficiency of CO2 within this formation. Empirical studies underscore the transformative impact of CO2 injection and mineralization on basaltic rock. Beyond the immediate storage of carbon dioxide, these processes induce changes in critical rock properties. Alteration in rock strength, porosity, and permeability are observed, influencing the overall behavior of the geological reservoir. Additionally, the interaction of CO2 with mineral can lead to the formation of cracks and the dissolution of mineral, adding layers of complexity to the evolving geological environment. The metamorphosis of basaltic rock due to the CO2 injection has profound consequences for the overall integrity of the geological storage system. The changes in porosity, permeability, and rock rigidity are indicative of the dynamic nature of the subsurface environment under the influence of injected CO2. Assessing the evolving characteristic of basalt formation is crucial for comprehending how CO2 is stored, released, and potentially transported within the reservoir. This deeper understanding is indispensable for designing effective CCS strategies and ensuring the sustained containment of CO2 over extended periods.
Okay, next we go to with the CO2 injection into basalt. So basically we have five process, which is site characterization, well drilling and injection, geochemical interaction, monitoring and verification, and long-term stability. So basically, CO2 injection into basalt formation involves the process of introducing carbon dioxide into subsurface of basalt reservoirs. Okay, so the first process is site characterization. So basically, the purpose of to do site characterization is to assess the geological properties of the basalt formation, including the porosity, permeability, mineral composition, and fracture patterns. And then after that, we go to the second process, which well drilling and injection. So basically, wells are drilled into the basalt formation to provide access for CO2 injection. Then once the wells are in place, carbon dioxide is injected into the subsurface reservoir under controlled pressure. And then the third process is geochemical interactions. So upon injection, the CO2 will interact with the pore fluids and mineral within the basalt formation. So this interaction can lead to process such as mineral dissolution. The fourth process is monitoring and verification. So the continuous monitoring and verification are employed to assess the behavior of the injected CO2 within the basalt reservoir. Then this includes monitoring changes in pressure, temperature, geochemical composition, and potential CO2 leakage pathway. And then the last process is the long-term stability. So the long-term stability and containment of the injected CO2 within the basalt formation are evaluated to assess the effectiveness of the storage process.
Alright, so the next one is the kinetic of mineralization reaction between CO2 and basalt. So as our project assignment that focuses on reactions injection of CO2 into the basalt formations, so I will explain more about how the kinetic of process mineralizations injections CO2 into basalt formation. So I can recap four factors that involved in these kinetic mineralization reactions. So the first one is activity of basalt minerals. Second one is monitoring and modeling. Third one is influence of water, and the last one is reaction rates. So basically, the kinetics of mineralization reactions between CO2 and basalt minerals actually plays a crucial role in assessing the carbon storage potential of basalt formations. So these reactions actually involve the chemical transformation of CO2 into stable maneuver to intersections between basaltic rocks. So this slide will explain more about the factors that important to consider when we investigate or when our group study about the kinetics of mineralization reactions. So as I recap just now, the first one is reactivity of basalt minerals. So the reactivity of basalt mineral, which is with CO2, actually is a key factor in determining the kinetics of mineralization reactions. So to determine the kinetics, the first one, the reactivity of basalt mineral itself is a main factor to injections process CO2 occurs into basalt formation. So these minerals can react with CO2 to form stable carbonate mineral to a series through a series of chemical reactions. So the second one is reaction rate. So the first one is reactivity. So not to forget the reaction rate of injection of CO2. So the rates at which mineralization reaction occur, including the resolutions of basalt mineral and also the precipitations of carbonate mineral itself. So it can be influenced by the factors such as temperature, pressure, and also the availability of water that will influence or give the effects to the reaction rate. And the third one is the influence of water. So actually the water acts as a medium for the dissolutions of minerals and the transport of dissolved ion. So as we know, when there are there are interaction between a few ions or few bonds. So actually the presence of water is very important to make sure the dissolutions of mineral can occur in the process. Okay, so the influence of water is very essential for the precipitations of carbonate mineral to form a stable carbonate minerals at the process. And the last factor is monitoring and modeling. So this includes the assessing changes in minerals compositions, porosity, and also permeability over time. So as we can see the figure that I have attached in this slide. So if we can see, there are four phases, which is the first one includes the phases between interaction water, H2O, and also carbon dioxide. So the interaction will process to the forms of carbonic acids. So the carbonic acids will include the interactions between the bonds of bicarbonates, hydrogens, and also carbonates. So these three forms of ions actually can involve to the acidic water. So the acidic water breaks down silicates minerals. So this breaks of acidic water actually will involve between interaction between magnesium and carbonates to form the solid stable carbonate minerals. Okay, so after we see the factor of mineralizations of reaction between injection of CO2 and in form of basalt formation. So there are a few chemical reactions that also include or processes in these phases, which is if you can see in this table, our group are summarized, will summarize a few chemical reactions that that requires a few reaction sequences, which is dissolutions and also precipitations lah. Okay, so if you can see the chemical reactions that occurs, so if we can see the chemical reactions that occurs involve the basaltic glass, phosphorides, dioxide installations, and also car plagioclase. So these chemical reactions actually refers to the two main reaction sequences in injection CO2 into basalt formation, which is dissolutions and precipitation. Hence, there are a few potential minerals for carbon mineralizations that occur in these phases of injection CO2. So there are a few solid type, which is wollastonite, phosphate, serpentines, and also anotites, and also basaltic glass that occurs in these phases of injection CO2. So in this table also, there are a few chemical formula that we have attached with the tones required to sequester 1 ton of carbon when CO2 inject in the basalt formation. So from this value of tools required, we can see that the serpentines crystallites that have the higher or the best value for potential minerals that occur in the injections of CO2 in the basalt formations. So next, we go to carbonate mineral produced that precipitate. So there are a few carbonate minerals that will produce after the injections of CO2 in basalt formations. So there are a few minerals that we have summarized in this table, which is including calcites, magnesites, downsonites, siderites, and also anthracites. So these minerals that we have studied in a few research. Okay, so these minerals that give a few value of mass that produce over proton that in injection of CO2. So if we can see the higher value that consists in this mineral is downsonites, which is it give the higher volume in produce per ton C in injection in basalt formation. So that we can recap, it may be the best mineral that involved in CO2 injection into basalt formation. So this actually occurs or this includes in our kinetics mechanism in CO2 in our basalt formation. So I will pass my presentation to the next presenter.
Okay, so next we move to analysis of the long-term stability of CO2 in basalt formation. So the long-term stability of CO2 storage in basalt formation is a critical consideration for assessing the feasibility of this approach for
for reducing the greenhouse gas emissions. While basalt formation have been identified as suitable for CO2 storage due to their mineral composition and reactivity, there are potential risks associated with the long-term stability of stored CO2. So one of the potential risks is re-release of stored CO2 due to geological events such as earthquakes or volcanic activity. While basalt formations are generally considered stable and less prone to seismic activity, there is still a risk of reactivation of pre-existing faults or fractures that could lead to CO2 leakage. Additionally, volcanic activity could potentially release stored CO2, although the likelihood of this occurring is considered low. So next is induced seismicity. So the injection of large volume of CO2 into basalt formation may induce seismic activity, while the majority of induced seismicity associated with CCS is low in magnitude. There is a risk that larger events could occur, potentially leading to damage to infrastructure or compromising the integrity of the storage site. So next is the next potential is CO2 leakage due to change in the physical and chemical properties of the basalt formation over time. So CO2 injection and mineralization can lead to change in rock strength, porosity and permeability, which could potentially affect the long-term stability of stored CO2. However, studies have shown that basalt formation have a low risk of leakage due to rapid carbonate mineralization, which can effectively trap CO2 in the rock matrix. So for the next potential risk is reservoir compaction. So basically the injection of CO2 may alter the stress and pressure condition within the basalt formation, potentially leading to reservoir compaction. So this compaction could affect the porosity and permeability of the formation, influencing the long-term storage capacity and integrity. For the next risk is abandoned wells and infrastructure. So the existing abandoned wells or infrastructure in the vicinity of the storage site may provide pathways for CO2 migration if they were not properly plugged and abandoned. So this pathway could compromise the long-term stability of the storage system. And for the last risk is climate and environmental change. So this change in climate patterns, extreme weather events or natural disaster could impact the stability of the storage system. So for example, increase in precipitation or temperature changes might influence the movement of fluids within the geological formation. So basically to mitigate this risk, it is important to carefully evaluate the geological properties of basalt formation and monitor CO2 storage over the long term. So this includes ongoing monitoring of CO2 plumps and potential leakage, as well as regular assessment of the physical and chemical properties of the basalt formation. So additionally, it is important to consider the potential for reactivation of pre-existing faults or fractures and to carefully select storage sites that are less prone to seismic activity.
Okay, next. Okay, next we go to the case study that we have implemented of this approach. So basically, we have two projects. For the first one is cutfeed project. So basically, the location that cutfeed project occur is launched near the Hareez geothermal power plant in southwest Iceland. So the objective for this project is to demonstrate the feasibility and effectiveness of storing CO2 by accelerating its transformation into solid mineral. And then for the injection site, the project is located near the Hareez geothermal power plant. And then the CO2 will be captured from the plant's emission and then will be injected into basaltic formation at the depth of 400 to 800 meters. And then for the injection process, the CO2 will be captured from the geothermal power plant. Then it will be pressurized and injected into the basaltic reservoirs. And then the injected CO2 will be interacts with the basaltic rock and then leading to mineral dissolution and the subsequent formation of stable carbonate minerals. And then for the monitoring verification, the CutFit project basically incorporates comprehensive monitoring and verification protocols to assess the behavior of the injected CO2. And then for the result and the impact of this project is basically the project has demonstrated promising result with the successful mineralization of injected CO2 within the basaltic reservoirs. So this innovative approach has the potential to contribute the global effort to mitigate climate change by securely storing CO2 in stable and permanent form. Okay, the next one is the Walula project. So basically, the location and geological setting for this project is situated within the Columbia River flood basalt, which offer a unique geological environment for CO2 storage. So the basalt formation in this region provide favorable condition for mineral trapping of CO2. So the four injection strategy in this project is the Walula project involve the injection of pure liquid CO2 into the basalt formation. Then this injection strategy aims to facilitate the interaction of CO2 with the basaltic rock, that leading to the mineral carbonation and the long-term storage of CO2. And then for the characterization and monitoring, so the comprehensive characterization and monitoring efforts are integral to the project. So these activities include the assessment of hydrogeological properties of the basalt, as well as the implementation of monitoring techniques such as well logging, seismic imaging, and geochemical analysis. And then for the research and validation, the Walula project has contributed to research endeavors aimed at validating the effectiveness of CO2 storage in basalt formation. And then the impact and the future prospect from this project is basically has demonstrated the viability of CO2 storage in basalt formation, that basically highlight the potential of this approach to contribute to global effort to mitigate climate change. And then the findings and experience from the Walula project have implications for the development of large-scale carbon storage initiative in basaltic reservoirs. Okay, so next conclusion.
Alright, in conclusion, the global ubiquity of basalt and its versicular texture, conducive to favorable injectivity and storage, position it as a promising contender for carbon capture and storage. However, the selection of suitable basaltic rock presents challenges, necessitating careful evaluation due to variation in petrophysical and mechanical properties, rapid mineralization, and the intricate utilization of the heat of reaction. Estimating storage capacity, injectivity, and containment in basalt formation requires sophisticated modeling to account for dynamic mineralization and evolving rock properties. Ongoing research and technological advancement are imperative to address these challenges, ensuring the effective deployment of basalt-based CCS strategies. A comprehensive understanding of basalt's geological and geochemical behavior will not only enhance carbon capture prospect but also contribute to broader the goal of sustainable and efficient geological sequestration of CO2, underscoring the need for continual refinement of strategies on a global scale. That's all from us. Thank you.